This is Unit 3, Partial Derivatives, Chapter 14, Section 14.3. So, on a hot day, extreme humidity makes us think that the temperature is higher than it really is, whereas in very dry air, we perceive the temperature to be lower than the thermometer indicates. The National Weather Service has devised the heat index, also called the Temperature Humidity Index, or humidex in some countries, to describe the combined effects of temperature and humidity. The heat index is the perceived air temperature when the actual temperature is T and the relative humidity is H. So we can write this as I is a function of temperature and humidity. So looking at this table, this is an excerpt of a table of values compiled by the National Weather Service. If we concentrate on the highlighted column of the table here, that corresponds to a relative humidity of H is equal to 70%. And then we're going to consider the heat index as a function of the single variable T for a fixed value of H. So for example, G of T is equal to a function of T at 70. Then G of T describes how the heat index increases as the actual temperature T increases when the relative humidity is 70%. The derivative of this function when T is equal to 96 degrees Fahrenheit, for example, is going to be the rate of change of I with respect to T. So we can write that as G prime evaluated at 96 degrees, so that's here, is equal to the limit as H goes to 0 of G of 96 plus H minus G of 96 over H, which is equal to the limit as H goes to 0 of F of 96 plus H 70 minus F of 96 70 over H. So we can approximate G prime of 96 by using the values in table 1 by taking H is equal to 2 and negative 2. So if we approximate these values, we have that G prime of 96 is approximately equal to G of 98 minus G of 96 over 2, which is then going to be F of 9870 minus F of 9670 over 2. And pulling these values from the table, so let's go to the table. We have 98 and 70 is going to be 133, and 9670 is going to be 125. So we have this is equal to 133 minus 125 over 2, which is equal to 4. We can also approximate G prime of 96, by looking at G of 94 minus G of 96 over 2, which will be the same as F of 94 70 minus F of 96 70 over 2. And then scrolling back up and let's look at the table, we have F of 94 is 118, and again F of 96 is going to be 125. So we have 118 minus 125. And this time our change is going to be negative 2. So I'm going to go ahead and put some negatives in here. And we have 3.5. So averaging these values, we can then say that G prime of 96 is approximately 3.75. This means that when the actual temperature is 96 degrees Fahrenheit and the relative humidity is 70%, the apparent temperature or heat index rises by about 3.75 degrees Fahrenheit for every degree that the actual temperature rises. So now let's look at the highlighted row in Table 1, which corresponds to a fixed temperature of 96 degrees Fahrenheit. The numbers in the row are values of the function g of h, which is then going to be a function of 96 and h, which describes how the heat index increases as the relative humidity h increases when the actual temperature is 96 degrees Fahrenheit. The derivative of this function when h is 70% is the rate of change of I with respect to h when h is 70%. Or we have g prime of 70 is equal to my limit as h goes to 0 of g of 70 plus h minus g of 70 all over h, which is equal to my limit as h goes to 0 of f of 96, 70 plus h, minus f of 96, 70, all over h. So by taking h to be 5 and negative 5, we can approximate g prime of 70 using the tabular values. So again, we will have g prime of 70 is going to be approximately equal to g of 75 minus g of 70 over 5, which is f of 9675 minus f of 9670 over 5. And again, let's scroll up and look at these values. So we have f of 9675 is 130, and f of 9670 is 125. So that's going to be 125 minus, 130 minus 125 over 5, which gives me 1. We can also use g prime of 70 can be approximately g of 65 minus g of 70 over negative 5, which is f of 9665 minus f of 9670 over negative 5. We know that this is 125 over negative 5. We scroll up and we find that 9665 is 121. So 121, and we have 0.8. Averaging these values again, we have g prime of 70 is approximately 0.9, which says that when the temperature is 96 degrees and the relative humidity is 70%, the heat index rises by about 0.9 degrees Fahrenheit for every percent that the relative humidity rises. Okay, so in general, if f is a function of two variables x and y, suppose we let only x vary by keeping y fixed, saying y is equal to b, where b is a constant. Then we're really considering a function of a single variable x, namely g is equal to a function of x and b. If g has a derivative of a, then we're going to call it the partial derivative of f with respect to x at a and b, and we're going to denote it as shown in equation 1. By the definition of the derivative, we're going to have that g prime of a is equal to the limit as h goes to 0 of g of a plus h minus g of a all over h. And so equation 1 then becomes f sub x of a and b is equal to my limit as h goes to 0 of f of a plus h b minus f of ab all over h, which gives us then equation 2. Similarly, if we are taking the partial derivative of f with respect to y at ab, we're going to keep x fixed at x equals to a, and then we're going to find the ordinary derivative and of the function g of y, and we're going to get equation 3. With this notation for partial derivatives, we can write those rates of change that we found previously as f of t evaluated at 9670 is approximately 3.75, and f sub h of 9670 is approximately equal to 0.9. If we now let the point A and B vary in equations 2 and 3, f sub x and f sub y became functions of two variables. So if f is a function of two variables, its partial derivatives are the functions f sub x and f sub y, as defined as shown. Similar to single variable calculus, there are many alternative notations for partial derivatives. For example, instead of f of x, we can write the partial of f with respect to x, or the partial with respect to x of let me rewrite this, f of xy, or the partial of z with respect to x, where z is defined as your function of x and y. Similarly, we can write similar notations for the partial of f with respect to y. We will have f sub y, the partial with respect to y. These two notations are rarely used, but occasionally do show up. And if you're going to be using Mathematica, you will need those.